this part of the problem, the last part, we're going to check the orthonormality between the wave functions, the excited states that we found in the previous parts of the problem. And so we can already tell, and then it was hinted at in the problem itself, that to exploit the fact that some of these are even and some of these are odd in order to not have to do the rest of the integrals. For example, and if we look at each one of the wave functions and the way it's designed, we know that the exponential is an even function. So this is, of course, an even function. Since we have an odd x sitting out here, this becomes odd. And then this is an even, and this is even. So when it multiplies one, the whole function ends up becoming even. So if we can even look at these in terms of just drawing them out, we can tell that which ones are odd and even. And again, we found the general forms of these, when we drew these from the previous problems, it wasn't very good, but we drew these from the previous parts of the problem here. And so now if we will go ahead and look at what happens whenever we check the orthonormality, which is just a fancy way of saying whenever you take the overlap or do the integral of one complex conjugate and another, so n and then m over all space, it's going to be equal to 0 unless n and m are actually equal to each other. But so we can go ahead and rule out this one multiplied by this one, because that will make an odd function, and the integral of an odd function is always 0. And then we can go ahead and rule out this one right here, these two multiplied by each other, because that's going to be 0 as well. But now the question is, what about the ground state and the second excited state, these two even functions? Does the integral of those two actually equal 0? Are they actually orthonormal? So we're actually going to have to crank out the integral on our own, but we do have a sense that these are probably going to be orthonormal because, I mean, the wave functions came from the textbook. So in an effort to save some time, I'm just going to go ahead and copy and paste these wave functions. So this is the second excited state, and then this right here is the ground state. And again, so the complex conjugate of the second excited state is not going to have anything fancy to do with it because there's no complex terms in here, so it's just going to end up being the same. So now that we go ahead and crank this integral out, actually, let's go ahead and pull the constants out. I'll identify the constants. So this is a constant, and I think, oh yeah, here's another constant here. So that'll just end up turning into a square root. So we'll have 1 over the square root of 2 times that glob of constants here. Okay, now let's go ahead and distribute that integral. Let's see here, x squared, and then our exponential m omega h bar x squared over dx minus, and that's going to be just a pretty simple exponential here, omega h bar squared dx, end bracket. Okay, so now we're going to go ahead and attack these two integrals here. I'm going to go ahead and bring down the constants. I'm just going to leave it like that because I guarantee whatever's going to end up here is probably going to be 0, assuming that quantum mechanics works out. So these integrals are kind of tricky. You can put them in the calculator, integration by parts or whatever, not really that one for integration by parts, but this one. Or you can look them up in the table. These are going to be common integrals that we're going to be using a lot. So I'll just go ahead and walk through them. So let me just go ahead and pull out the constant right here from out in front of the integral here. And now let's walk through this. So this integral, the x squared e to the exponential, it's always going to be pi, the square root of pi over 2, which was the exponential term, or the powered term, times the what's the inverse of what's inside of or what's being multiplied by the x squared in the negative exponential. Again, I wouldn't recommend memorizing this right now. Just over time, you'll get to know this term, this whole integral as well. And then it's going to be the square root of what's inside there, which is the h bar m omega square root, right? So we'll go ahead and mark off our like terms. All right, and then we have the pi actually goes into the inside the square root here, but that's okay. And then this integral here ends up being just the square root of this, the inverse of what's inside here, times square root of pi. So we'll just go ahead and bring the square root of pi in here. And again, like I said, I would recommend using an integral table here, but after a while you'll realize you'll just memorize these. Okay, so we have the square root of pi times h bar over m omega, square root of pi times h bar m omega. Doesn't matter what the constants out here are front, because everything that's inside here just goes to 0. And that makes the entire term end up being 0. Exactly what we thought. So the orthonormality actually checks out for all of them. So turns out the theory's right. The simple harmonic oscillator and the ladder operators work out as expected.